Hi everybody, welcome back to Environmental Organic Chemistry with Dr. Lisa. We're going to finish up this lecture about photolysis by looking at these two flowcharts that help you decide. It's like a decision tree for help you figuring out what's going to happen to your chemical if it does get released into the troposphere. So the first of these is the fate of gases emitted to air. Get my pen out. The fate of gases emitted to air. And so the first question is the gas water soluble or fully oxidized? What this is saying is it pretty polar, like CO2 is fully oxidized because the carbon is in the plus 4 oxidation state, can dissolve into droplets of rain and be rained out. So if that's true, if yes, then your gas will just be returned to the Earth's surface as a relatively polar water-soluble compound. It'll get rained out. And also, if it has a low vapor pressure, as most water-soluble compounds do, it will also stick to particles in the gas particle partitioning, and therefore not much of it will stay in the atmosphere. More of it will stick to particles and get rained out. If that's not true, then the question is, does it photodecompose? So what this is really asking is, does your chemical undergo direct photolysis? If the answer to that, and how would we know? Well, we would look for the n and the pi orbitals. If a compound has both unbonded electrons, lone pair electrons, and double bonds right next to those lone pair electrons, then it can do a n to pi star transition, and therefore it can probably undergo direct photolysis. So we say yes, and then our chemical goes over here and starts to react with sunlight and produces free radicals. If it can't undergo direct photolysis, then the question is, does the gas molecule have multiple bonds that OH can add to? In other words, hydroxyl radical is probably the next best thing to direct photolysis, and we know that hydroxyl radical prefers to add to double bonds. And so the first question is, does it have a double bond? If so, yes. Well, then hydroxyl radical adds on to the chemical and forms, you guessed it, a free radical. If the answer to this question is no, then we ask the question, does the gas have molecules? Does it have a hydrogen atom that OH could abstract? Because again, we said if the compound can't react by direct photolysis, then it's going to have to go by indirect photolysis. Hydroxyl radical is the most common reactant in the troposphere, and it likes to add double bonds first. If there's no double bonds, then will abstract a hydrogen atom. So if the chemical does have hydrogen CH bonds, then hydroxyl radical will abstract that hydrogen, and again, you will get free radicals produced. And only if the answer to all of these questions is no, do we conclude that the gas is inert and it will rise into the stratosphere. And we had a good example of that. The first part of the class, we spent a lot of time talking about Freon 12, right, which was dichloromethane. Okay, so is it water soluble or fully oxidized? Not particularly soluble. Actually, in this case, the chlorine is fully oxidized, but it's not water soluble. Does it photodecompose? The carbon-fluorine and carbon-chlorine bonds are too strong, will not react unless the sunlight wavelengths get well below 290 nanometers. So at the troposphere, no. So the answer to this is no. Does it have double bonds that hydroxyl radical can add to? Nope, no double bonds here. Does it have hydrogens that the hydroxyl radical can abstract? No, does not. So this is the lone chemical, or one of the rare chemicals, for which all these answers are no, and it's inert and will rise up out of the troposphere all the way to the stratosphere. Remember, we talked about the fact that horizontal mixing is relatively easy, but vertical mixing, especially in the atmosphere, is much slower. So this chemical will disperse horizontally, and then because it stays in the atmosphere for so long, at least some of it will get mixed vertically and end up in the stratosphere. Okay, so this is our decision tree of what happens to a chemical when it is released into the atmosphere. And then the next decision tree is, what happens to those radicals? Remember here we said lots and lots of free radicals are being produced. Well, what happens to them? Question number 1, does the radical have a peroxy bond? Remember, that's R, O, O, O dot. That's a peroxy. Is it a peroxy bond? If so, then it oxidizes nitric oxide. That's when NO takes that extra oxygen off and becomes NO2. Remember, we said that's part of the ozone cycle. This is important chemistry, okay? And then you get an O-centered, an oxygen-centered radical. Okay, if it's not of a peroxy type, does it look like this? Does it have a terminal CH2O dot? If so, then you can split this carbon-carbon bond right here. And what you're doing is you're going to split off this thing, which is formaldehyde, COOH, with the two H's here. Okay, that's formaldehyde. So formaldehyde splits off, and then this thing is now a carbon-centered radical. If none of those things are true, then can hydrogen removal from HX convert it to this double bond? If so, then even peroxy, even oxygen, is strong enough to abstract that hydrogen because you're leaving behind a very stable product. So in that case, even oxygen is strong enough to abstract that very weakly held hydrogen, and you get a peroxide radical, and then your compound is converted into this double bonded thing, which is now not a radical. And so to determine the fate of this thing, you would go back to this previous flowchart and ask what happens to that product as you go through this flowchart. Okay, and then if the answer to all of these things is no, then you have, every other radical in the world, O2 just adds to the radical to produce a peroxy. Okay, so this, I find these decision trees really helpful and useful. I don't know how much you like them. But now let's think about this. Let's do an example. And I'm going to try something with a high degree of difficulty, which is that I'm going to draw something on the paint board. And you're going to have to really trust me here. Oh, that's just too big. Hold on. Let's make this much smaller. Is that better? No, still too big. Make it even smaller. There we go. So here's our compound. Yeah, we're zoomed too far in. I need to zoom out a little bit. Here we go. Better. I did practice this, and then I zoomed in too much. Okay, so here's our chemical. Let's say our chemical is ethane. Here's ethane. Ethane is flowing through the world. Is it water soluble or fully oxidized? No. Does it photodecompose? No, because it doesn't have N or pi orbitals. Does it have multiple bonds? No. Does it have hydrogens that OH can abstract in an exothermic reaction? Ah, yes, it does. So we're going to draw it this way, and we like to draw a loop like this and say that hydroxyl radical comes in here and abstracts one of these hydrogens. So you get a water molecule here, and you get H2C CH3, and this is a radical right here. Okay. Okay, now we have a radical. Now we need to go to this flowchart. Is it a peroxy radical? No. Is it of this type? Nope. Does it have this weird functional structure? Nope. Therefore, the only thing left to do, O2 adds to the radical to produce a peroxy radical. Okay, so I can draw that. I will just draw O2 coming in here. I apologize for the crudeness of it, but it does get the point across. O. There's the radical part right there. CH2, CH3. Okay. Now what happens? Okay, I'll go back to my flowchart. Does it have a peroxy bond? Yes. Then it oxidizes nitric oxide. Ah, okay, so I can draw this, and we'll draw our little loop here. NO comes in. Sorry, just plain NO. And becomes NO2. Sorry for my bad drawing. Okay, so we now just have one oxygen here, still a radical. CH, and I'm going to draw this hydrogen here explicitly because that's important. CH3. Okay, still got a radical, so what happens next? Does it have a peroxy bond? No. Is it of this type? Well, lo and behold, look at this functional group. It is indeed of this type. If yes, then the carbon-carbon bond splits. So this carbon-carbon bond is going to split. What happens is one electron goes over here, and remember when we're drawing only one electron moving, we give an arrow with only one side of the arrowhead, and this electron comes in here. So those two electrons get together and create a double bond, and this electron goes over here and forms a methyl radical. So we'll draw this sideways now. So now we've got formaldehyde. Try to go too fast. I should slow down. Formaldehyde plus CH3 radical. Okay, sorry, it looks pretty bad, but it's a radical. Okay, so now what happens to this radical? Well, essentially it goes right back up here, except that it's now missing a methyl group. But it's a carbon-centered radical. It adds to oxygen, forms the peroxy, oxidized nitric acid, and then goes to form another molecule of formaldehyde. So what have we learned? We have learned that if you have long-chain hydrocarbons in the atmosphere, what happens is that the oxygen and the reactive oxygen species in the atmosphere basically combust them until you form a whole lot of formaldehyde, which is relatively polar and will rain out and partition onto particles and leave the atmosphere. And so this process, these free radical reactions, just chomp one carbon at a time off of your hydrocarbon, and eventually your chemical gets burned up completely. And this process is exactly the same process that happens during combustion. Like if you literally took a match and set ethane on fire, this is roughly what would occur, except that you wouldn't stop at just formaldehyde. The formaldehyde would actually oxidize all the way to CO2. But this photolysis product is basically just slow motion combustion. Same thing. Okay, so I find those two flowcharts to be really, really useful. I hope that you will find them useful as well. That concludes the lecture portion of the lectures on photolysis. After this, there's going to be some example problems, and then guess what, baby? You're done. The only thing left for class in this semester is to go do some review of different types of chemical reactions and which molecules can undergo those reactions and which ones can't. So I will see you on the other side.